Hello. In this video, I demonstrate two approaches that are available in Stata for analyzing panel data. Both approaches assume random intercepts and involve estimation of model parameters using maximum likelihood estimation. The first approach I demonstrate is a random effects panel regression using the xtreg command. The second approach I demonstrate is a mixed effects regression using the mixed command. The data I will be analyzing comes from the 2017 and 2018 college football seasons, where we have team data measured across years. The outcome variable is football power index as of the end of the two seasons. This variable varies over time. The time-varying predictor variables are red zone scoring percentage and schedule strength. We also have two time-invariant predictors, Power 5, which indicates whether a team is associated with a Power 5 conference, and stadium size. The data are organized in long or vertical format, with each row representing a given year for a specific team. The values of the time-varying outcome and predictors vary over the 2 years, and the values of the time-invariant predictors, which are Power 5 and stadium size, are constants across the 2 years, but vary between the teams. So before we actually carry out the analysis, let me note that I'm going to have the data for these analyses available for download underneath the video description. And in addition, we'll also have the text file that you see right here available for download as well. So let's also take a quick look at the data as I had just described it. I'm going to go under Data, Data Editor, and you'll just go to Data Editor, Browse. So you can see ID and Team. So you can see that for row 1 and row 2, we have Air Force. And so, and we have basically a numerical identifier for Air Force, which is 1. For Akron, we have 2, and so forth. So our outcome variable is FPI post, and you can see it varies between the 2 years. So this is 2017, 2018 right here for Air Force. Then for Akron, we have 2017, 2018, and so forth. So it's organized that way all the way down. So that is our outcome variable. Our predictor variables are red zone scoring percentage and schedule strength. And you can see that these values differ across the years as well within teams. So there's Air Force red zone scoring percentage for 2017, 2018, schedule strength for 2017, 2018 for Air Force, and so forth. Now, if we go over here to stadium size and Power 5, you can notice that the values do not change across the 2 years. And so these are constants for the team across the 2 years. So these are basically our time invariant predictors. Okay, so with that in mind, let's go ahead and begin our analyses. So I'm going to actually click out of this, and we will start off with the random effects panel regression. So to do this, first off, we need to use the xtset command in order to let Stata know that we're working with panel data. And our team identifier variable is followed. So you can see right here I have it set as ID. And so that is basically this variable within our data set. So what we'll do is we're actually just going to go down to the command line right here and just type in xtset and then ID. And there you go. So now we are letting Stata know that we're working with panel data. Okay, so then the next step, what we'll do is we will use the xtreg command followed by FPI post. That is our dependent variable. So you can see that it's also showing up right here on the right. Then we have our predictor variables. So there's red zone scoring percentage, schedule strength, stadium size, Power 5, followed by a comma and then MLE to designate that we are going to be carrying out our panel analysis using maximum likelihood estimation. So without spending a lot of time typing this, what I'm going to do is actually just copy all of this and paste it into the command line in Stata and then hit enter. And so now you can see that we've run our panel regression. So looking at our output, we can see that we have red zone scoring percentage. These are the regression coefficients, standard errors, z values, and p values. So we can see that red zone scoring percentage is associated with a higher FPI at the end of the season. and that relationship between red zone scoring percentage and FPI is statistically significant. Schedule strength, you can see there's a positive coefficient, so basically higher levels of schedule strength or more difficult schedules are associated with higher FPI at the end of the season, and so that's a significant predictor as well. So these were our two time-varying predictors. These are our two time-invariant predictors. So we have stadium size and Power 5. So you can see that stadium size was a positive and significant predictor of FPI. And then we also have the Power 5 variable, and you can see there's a negative coefficient here, and there's statistical significance. We can also see, too, up here we have the LR chi-square with 4. And basically, the 4 is designating the number of predictors in our model. So this is essentially a likelihood ratio chi-square test, testing a null model, which essentially includes only the intercept, versus our full model that contains the full set of predictors. And so you can see right here, this is the likelihood ratio chi-square value, and then our p-value. So given that the p-value is less than 0.05, is basically indicating that our full model containing the complete slate of predictors represents a significant improvement in fit over a null or intercept-only model. So next, what we're going to do is use a post-estimation command to obtain the AIC and BIC, and we're not going to do anything in terms of interpreting right now, but I'm just going to go ahead and put this in here as well so that we can get that information. So you can see we've got a Keiki's information criterion and Bayesian information criterion, and these are the values associated with this particular model. So now moving on, let's run the mixed effects model. So we're going to use the mixed command right here, and you'll notice that we have FPI post, red zone scoring percentage, schedule strength, stadium size, Power 5. All of those are in the same order pretty much as what we had up here. The main thing is that following either the xtreg or the mixed command, you have to have your dependent variable, and then really the order of the independent variables doesn't matter. Okay, so next, following Power 5, which is the last of our independent variables, we have two vertical lines right here, followed by ID, basically our team identifier variable, and then followed by a little colon. So let's go ahead and copy this and paste it in to the command line and hit enter. And so now we've run essentially a mixed effects model using maximum likelihood estimation. Okay, so the first thing to note is up here we have the Wald chi-square test, and basically this is indicating that our model is a good fit to the data. So if this is statistically significant, that's an indicator of good fit. Now, in terms of the comparison between the two models, if you look at the coefficients boxes right here in terms of our mixed effects model and then our random effects panel regression, you can see that the coefficient values are exactly the same. The standard errors are a whisper different, but they're pretty similar, as well as the z-values and the p-values. So in many respects, these are essentially equivalent values with a few differences here and there. Now, also note that the log likelihoods for the two models, this is from the mixed model right here, and then from the random effects regression model up here, you can see that those values are exactly the same, really basically reflecting equivalent fit. If we use the post estimation command and compare the results from our mixed effects model to our random effects regression model, you'll notice that we end up with exactly the same values. So there's the log likelihood again, there's the AIC and BIC, and those values are exactly the same as what we had up here when we ran our panel regression. Okay, so another thing to note is that because our random effects models essentially allow the intercepts to randomly vary across teams, then we can also have an estimate of the variance of the intercepts. So within our mixed effects models, this right here is the estimated variance of the intercepts. And you'll notice that if we look at the panel regression output, we have this value right here. And this is actually the standard deviation of the randomly varying intercepts. So if you take this number and you square it, you will end up with this number from our mixed effects model right here. Basically, giving us the variance of the intercepts. Now right here we have the standard deviation of the residuals given in this coefficient from the panel regression. If we square this number, we get the variance of the residuals that are presented below in the mixed models table. Okay, and finally, to drive home the point that we're really basically talking about equivalent models, let's go back up to the panel regression where we have the likelihood ratio test. And this, again, is basically testing whether the model containing the full slate of predictors represents a significant improvement over an intercept-only model, with the intercepts being allowed to randomly vary. So a way that we can essentially test this equivalence is just by running our mixed effects model with no predictor. So right here I've got the mixed command followed by the name of the dependent variable, our two vertical lines right here followed by our grouping variable identifier, which is ID, followed by a colon. We'll store the estimates from that model, and then we'll rerun the model containing our dependent variable and our full slate of predictors and so forth. And then we'll store those estimates as well and then carry out a likelihood ratio test involving the estimates from Model 1 and Model 2 right here. So let's go ahead and do this. So I'm actually just going to start off with our first model that includes no predictors and just allows the intercepts to randomly vary. So there's our first model right there, and then we'll go ahead and store the estimates from that model. So I'm going to copy this and paste it into the command line. And so we're good to go there. So now let's do the same thing involving the second model containing our full slate of predictors. And I'm actually just going to copy all of this and paste it into the command line as well. And there you go. So there's that model. So then we're going to carry out a likelihood ratio test using the estimates stored in M1 and M2. So that's why we have LR test and inside parenthesis M1 and then M2 right here. And then followed by a comma, then stats, and then space dir. So I'm just going to copy this, and we'll paste this into the command line as well and hit enter. And so there you go. And so notice that the results of the likelihood ratio test, first off, we have the assumption that Model 1 is nested within Model 2. So Model 2 is the full model containing all of our predictors. So we have a randomly varying intercepts, but we also have our fixed predictors within the model. Model 1 is just basically the random intercept model, so that's the nesting. And you'll notice over here we've got the likelihood ratio chi-square and the same value that we saw above with the likelihood ratio test with the panel regression and the same p-value. Once again, when we compare the log likelihood, the AIC, and BIC from our model, from our mixed effects model to the panel regression, we have exactly the same values. So that concludes this demonstration, and I appreciate you watching.